In this video, we're going to look at limits at infinity. What we mean here is that the variable is going off to either positive or negative infinity. So it'll mainly be a list of examples showing what happens, what we call the end behavior of certain functions. This graph is looking at the two functions of tangent of x and also the inverse tangent or the arctangent function. As you see here, we have that the limit as x approaches infinity of the arctangent function is pi halves, and the limit as x approaches the negative infinity of the arctangent function is negative pi halves. Looking at the blue graph through here. Again, as I go to the right side off to infinity, the graph approaches the horizontal line x equals pi halves. As I approach the left side of the graph to infinity, I approach the graph of y equals negative pi halves. Now the graph of the tangent function, or at least one portion of it, is shown here for contrast. Now the values are going off to infinity, as you see labeled here, but the value of x is only approaching a value here. It's approaching pi halves. So the variable here is not going off to infinity. So this would indicate that we have a vertical asymptote for the tangent graph. This again is kind of a zoomed in version of the arctangent function, or at least something similar to it. As x approaches infinity, it goes this direction, the f of x, or the y coordinate here, gets higher and higher and approaches the value of L. The expression can be written simply as this. As x goes larger and larger to infinity, f of x goes to L. And we simply write the limit equals L. If we let x go to negative infinity, however, the graph goes downhill towards the value of y equals m and get the expression shown here. Again, pause the video here if you need to. This is simply a rehash of the statement about horizontal asymptotes. The idea is that we're looking at what happens to the graph as x approaches infinity, or similarly what happens as x approaches negative infinity. If we have that happening, we would say that the values are horizontal asymptotes, as we see in the next slide. Here, as x approaches positive infinity, the graph approaches the line of y equals 2. It also approaches the graph of y equals 2, or the line equals y equals 2, as x approaches negative infinity. So both the left and the right hand limits of the function are 2. So we would say that the graph here of y equals 2 is a horizontal asymptote. This function has a trig function in play. As the x variable gets larger and larger, this value in the numerator only goes between 1 and negative 1, so it never gets very large. However, the square root of x, as x gets very, very large, becomes a very large value, and a small number over a large value becomes very, very small. So 5 plus something becomes something near 5. Now, since this could be positive or negative, it's either sometimes above 5 or below 5, but as x goes this direction, the graph does get smaller and smaller. It's not as easy to see as you might be helpful, but this graph should be getting tighter and tighter to the line, which makes this a horizontal asymptote. This graph shows the end behavior of an odd degree polynomial. As x approaches infinity, the graph goes uphill. We write down the expressions shown here. As x approaches negative infinity, the graph goes downhill. Write the expressions shown here. So this is simply a couple of examples of what we see here, where the limits approach infinity or negative infinity as the x approaches infinity or negative infinity. This happens quite often with power functions or polynomials. If you look at even degree polynomials, the graphs always go uphill on the left and right. However, for odd degree polynomials, we have graphs going downhill on the left but uphill on the right. The fact that it gets tighter and tighter from smaller to larger values of the variable or to the value of n is true, but not what we're looking at in this example. In all cases, the graph's going uphill forever and are going downhill forever on each side. Over here, they always go uphill. This is simply a statement of what happens to these different power functions and what their implications are based on some other things. If we look at a polynomial given by the expression here, then the power functions behave just like we mentioned in the previous slide, both here and there. If I look at inverse functions, because of things we'll see later, they always go to 0, because the bottom is blowing up to either positive or negative infinity, but 1 divided by either case will go to 0. The polynomial behaves exactly like only the leading term. Again, in this expression, we have this term plus all of this stuff. But in the limit, as x approaches positive or negative infinity, only the things circled in purple are going to matter. The stuff here in red will be inconsequential compared to the size of this term. So these two limits should have the same value, and it'll behave just like the term here, depending on the sign of an and the even or oddness of n. This one is an example of what I just mentioned. We have the polynomial 3x to the fourth minus 6x squared plus x minus 10. As I look at the graph of 3x to the fourth being a positive coefficient, it should behave just like x to the fourth. Being it's an even power here, it's going to be going up from both directions, getting both the statements I see here and here. This one shows the idea of negative 2x cubed. The negative means we're going to reverse the value, what happens for x cubed. X cubed looks something like this, where it has a down on the left and an up on the right. Because of the negative sign here, this graph is going to have an up on the left and a down on the right. This one shows a couple of different things, but has the idea that if we look at a rational expression, some things could be done with kind of a formulaic sense. In this rational expression, the degree of the top is 1 and the degree of the bottom is 2. So as x gets very, very large, the bottom is much larger than the top. So we're dividing a smaller thing by a larger thing, which should give us small values. The limit from both the left side going to infinity, negative infinity, and the right side going to positive infinity are both 0. This one shows an expression where the values here are the same, x to the fourth and x to the fourth, so they grow at the same rate per se. Since eventually this term matters in the top and this term matters in the bottom, all of these terms become inconsequential, and I simply focus on what happens in this box here. And this box here approaches the value of 4. So the graph seen here also has the value of 4 in it, and that is going to be the horizontal asymptote of this function. This one shows an example when the degree of the top is larger than the degree of the bottom. In this case, the function will blow up to either infinity or in some cases negative infinity on both the left and the right. Again, you could have them match both up, you could have them both be down, you could have down then up, or even up then down. This one shows what happens if we have the degree of the top being exactly one more degree of the bottom, degree 2 over degree 1. In which case we get what's called a slant asymptote. The graph will actually approach this line as x gets larger and larger. However, the limit as x approaches infinity of f of x still equals infinity because it is going uphill. And if I look at the right side, or the left-hand side, the limit as x approaches negative infinity of f of x equals negative infinity. Again, because the graph is going downhill. This is a good time to pause the video. There's a lot of information on this chart. This talks about what happens with rational expressions or rational functions based on the degrees and signs of the different expressions. This is also found in the textbook and also online. But again, please feel free to pause the video and look at this material in depth. If you have any questions, please let me know. And this one is something that's what we would often call a rational-like expression. Because of the square root, things can be a little bit funky, but basically it has the same behavior. The bottom behaves like the square root of 25x to the sixth, or that being the value of 5x cubed. The top behaves like 10x cubed. 10x cubed over 5x cubed does appear to be the value of 2. But because of the square root symbol, we can get a plus or minus in certain cases. Though when x is negative, we actually get a value down here that a negative pops out somewhere in this expression, and we get negative 2. Okay, this will be much easier to do from a graph, so I don't think you need to see it from the function itself. This simply shows what happens for other types of functions we've considered. This is the natural exponential function. As x approaches negative infinity, the function decays to 0. As x approaches positive infinity, the function grows without bound. This shows, if I look at the inverse function of the exponential function, what's called the logarithmic function, the end behavior here becomes the end behavior here, and this becomes the end behavior here. So while this one, x was going to negative infinity and the value was 0 from above, here x goes to 0 from above and the value equals negative infinity. Similar statements can be made here, And I'll leave that at that. This shows that in behavior doesn't actually have to exist. Cosine, being that never ever gets close to anything, simply goes back and forth between -1 and 1. So in this case, going to negative infinity or positive infinity would not give a value as the x goes to that value. It goes to those limits. This simply shows what happens to log of x. As x gets really, really large, these values are taking off. The question is whether they actually go off to infinity or if these values are getting bound by something. So to sum up this information and to answer that question, if we look at the limit as x approaches infinity of log of x, it does go off to infinity. This is a good time to pause this and take notes here if you want to simply memorize what happens to the different end behaviors of both the exponential, the traditional exponential function, the decaying exponential function, and the natural logarithmic function. Thank you for watching this video. If you have any questions, please let me know.